I'd like to introduce Anandi Hira and Dr. Jim Alstead, who are our speakers tonight. I'd like to thank him in advance for joining us and sharing information about causal analysis and software and systems engineering with us tonight. I'm sure everybody's here, so has seen the meetup or other descriptions of their talks. So without further ado, I'd like to again hand it over to Anandi and Jim.
Hi, everyone. Thank you so much for joining us today. We hope that you enjoy our presentation. We are going to go over work that we have done for, I think, the past 2 years now. And let me just share my slides very quickly. All right. So we started this work when Jim and I were both PhD students at USC. And we also worked with Windsor Brown, who I think most of you may know, and Mike Conrad from SEI. Of course, he's not able to make it since he's on the East Coast. It would be really late for him right now. I have finished my PhD at USC, and I am now working at Technology Research. Jim, would you like to introduce yourself?
Yeah, I'm Jim Alstead. I also am a recent PhD from USC. Anandi and I are sort of PhD buddies. We both started our PhDs at the same time. We were both teaching assistants in the same course for, let's just say, for more years than we expected to be. And we both got our degrees within about a year of each other. I've been a long time software engineer, and my thesis topic is COSYSMO 3.0, a cost estimating model for systems engineering. And I would like to mention that by this time next year, I will have been an ACM member for 50 years. Back to you, Anandi.
Well, thank you for that. All right, so we've broken up this talk into 2 sections. And the first one is going to be an introduction on the causal inference framework that we have used for our research, for this particular research, not related to our dissertations, by the way. But I'm going to describe it to you at a high level so that you have an idea of what is causal inference. And then Jim is going to talk about how we applied it to the 2 data sets that we had access to. All right, so first, let's start with the introduction to causal inference. And by the way, this first about half set of the slides that I'm going to be going through have been adapted from CMU. Okay, so first let me explain what a causal model is. So and also how and why causal relationships are important. So usually when we have data, we might run correlation, and we'll see that 2 different things have high correlation with each other. So for instance, ice cream sales and shark attacks are highly correlated. And of course, we then would ask, so does that mean that ice cream sales causes high shark attacks, or vice versa? Maybe shark attacks cause high ice cream sales. And we want to understand how things work and what we could do to influence other things. So for instance, if high ice cream sales was causing shark attacks, then maybe we should reduce ice cream sales so that fewer people are getting attacked by sharks. So basically we want to understand causal relationships so that we know what we can do in order to influence a specific type of outcome. However, of course, we can tell that there's really no causal relationship between ice cream sales and shark attacks here. So you may have people that will sit and think about, so what is causing this high correlation between these 2 variables? And as we think about it, we'll realize that what typically happens in the summertime as the temperatures increase is people will go out to the beaches, go out where there can be sharks. They'll also go out and buy ice cream to cool down. So both of these activities are for them to cool down. So then we realize that actually there is no causal relationship between ice cream sales. It's that the hot temperature is causing ice cream sales to increase, as well as for shark attacks to increase. Now, typically, we need either domain experience or people that are thinking about it and have some understanding of the environment to come up with such a causal model. Or you may run experiments and use interventions and manipulation, for instance, in order to come up with your graphical model that explains how some environment interacts or behaves. So causal inference is a specific study that instead of having to use intervention and manipulation or depend on domain expertise to come up with a graphical model, it uses testable constraints in order to get to that graphical model. So it's trying to use data instead of depending on experiments, especially because in some environments, for instance, you might not have an idea of how things are behaving and what the causal structure is like, or you might not be able to run experiments. So for instance, in software and systems engineering effort, it's really cost prohibitive to try to run experiments. So that's where causal inference comes in. So what causal inference is doing is it takes your causal structure and it goes through understanding how causal relationships behave and defining them mathematically. So by using, for instance, conditional independence. And before everyone starts to get nightmares about their statistics classes or the probability classes that they have to take either in high school or college, let me just say, I'm going to try to explain everything as simply as possible. So you don't need to necessarily understand and remember any mathematical equations in order to understand the concept of this presentation. So again, we're using mathematical ways to define and explain causal relationships. And now we're going to use that to gather or to create our graphical model from the data. So that's what we build the theory or the algorithms on the causal structure to get back to a causal structure. Okay, so let me just define a couple of concepts here, and I'm going to try to define in terms of data so that it makes sense. I'm sure most of us have had to do at least some simple data work. So what does it mean if we have two variables, say x and z, are independent of each other? That means that x and z, variables x and z, are not correlated. We shouldn't see them have high correlation with one another. Now, if we add on the independence part, that means that x and z are independent condition on y. So what that means is for each and every value of y, x and z should not be correlated. So in terms of data, a lot of times we might filter or group our data based on the value of some other variable. So for instance, some variable y. So for each of those groups that we've created by filtering or grouping our data by y, we would see that x and z are not correlated. And that's what we mean if x and z are independent conditional on some other variable. Okay, so taking this a little bit further, in terms of a causal graph, variables x and z would be causally disconnected if they are independent, which means that x is not a cause of z, z is not a cause of x, and there should be no other common cause of both x and z. So there's essentially no trek between x and z. And not only should there be no direct trek between x and z, but they are also independent conditional any subset of the variable that of course doesn't include x and z. So that means that if we are saying that variables x and z are independent and there is no edge between them, no causal edge between them, then they are independent conditional on any variables in your data set or any combination of variables in your data set. Okay, so we can understand how we define causal relationships with independence and conditional independence, for instance, but how can an algorithm really figure out, without domain expertise, without a human giving it direction, what direction of causality you have in your data or in your graph? So the way that is done is by looking at the interaction of three or sets of variables. But for simplicity, we're going to look at the interaction of three variables. So three variables can interact with each other in three ways. You can have a chain. So you would have X causes Y, which causes Z. And then you may have a fork. You have some common variable Y that causes both X and Z. And then we have a collider. So in this case, Y, the other variable Y here, is a common effect of both X and Z. So what's really important is the differentiation between a collider and a non-collider in order to determine the orientation of our edges. And I'm going to explain why using some simple examples. So the first example here is one of a collider. So in a very simplistic way and not taking into account a lot of things, but in the case where we start our car in the morning, for the most part, you need to have not a full gas tank, but at least enough gas to start the car, and you need a live battery. So in this case, or at least for starters, gas and battery are independent of each other. Having gas is not going to affect whether or not your battery is in good health or not, if it's alive or not, and vice versa. But both independently of one another are needed to start your car. Now, if we condition on this variable car starts, and we say, okay, our car does not start. Now, in this case, when we condition on this variable, gas and battery are no longer independent. Because if I know for a fact that I should have enough gas, then there must be something wrong with the battery. Or if I know that I just replaced the battery yesterday and it is healthy, then most likely I ran out of gas. So now these two variables are no longer independent of each other. On the other hand, when we're working with non-colliders, and here's one example. So you could think of the coronavirus, for instance, where if you get exposed to it, eventually you may get infected, and eventually you may show symptoms of having contracted the virus. So we have a sequential or chain interaction here. And in this case, of course, exposure to the virus and symptoms are not independent, because eventually getting exposed to the virus is going to cause you to show symptoms. So these two in this case are not independent. However, if we now condition on this middle variable, infection, in this case, then when we do that, now exposure and symptoms are independent of one another. So this behavior holds for colliders and non-colliders. And of course, with the non-colliders, we have two different ways of being non-colliders. And this is just one example of the chain, but we also have the fork. So when the algorithm that is trying to determine the causal graph with your data, when we get to a point where we're testing out the relationship between three variables, what it first does is it's going to check are X and Z independent given some subset of the variables. So let's say some variable Y. If it finds that it is not independent, then we know for a fact that we have a collider. So that means that both x and z point into y. On the other hand, if we find that x and z are, did I say that wrong? So in this case, x and z are not independent conditioned on y. If we find that they are in fact independent conditioned on y, then we know that this is a non-collider. Unfortunately, we don't know exactly what type of non-collider we have. So we have three different options here. We have that it could be a chain in either one direction or the other. So x pointing to z or z pointing to x eventually through y. Or we have a fork where y points to both x and z. So given the options of how the algorithms can figure out what the orientations are, we have a few different options of the kinds of outputs we would get. In the first case, we would find that x1 and x2 are not adjacent. So that means that there's no causal relationship between the two. Then we would find that perhaps one variable is a cause of another variable. So x1 points to x2. And that can be done, again, when you have a collider. Or you have that you can see there is a causal relationship between the two variables, but you're not able to figure out which orientation is the correct one. So for instance, when you run into a non-collider, then that's represented with just a straight edge with no arrows. Or in other words, an undirected edge. All right, so that's just a brief introduction to the theory and how causal inference works. And I just want to point out at this point the difference between causal inference and causal analysis. So of course, causal analysis contains or consists of a large group of studies that can be considered causal analysis. So for instance, running experiments and figuring out what your causal graph is or what the causal relationships are. That's the type of causal analysis. And causal inference is just one study. Now, this was just a very brief introduction to the theory so you can understand how it works. And in my case, I thought what was most interesting was to understand how it differs from correlation. So, of course, while you can get into the more detail if you really wanted to, we're going to continue moving on, describing causal inference a little more. So there are two aspects to causal inference. You have causal search or causal discovery, and that's basically where you provide observational data, and the algorithms use the theory that I kind of discussed very quickly with you before to come up with that causal graph. So the algorithms try to determine what the causal relationships are with the observational data that you provided. And then the other aspect is causal estimation, and that is essentially providing a quantifiable influence on what the causal structure is. So basically creating a mathematical model that's based on your causal graphical model. There are two types of causal search algorithms. The first is called constraint-based. So constraint-based algorithms use conditional independence to determine which causal relationships exist in the way that I had described before. And then there's score-based. And score-based algorithms, instead of using the conditional independence, what they do is they do a step-by-step search and compare combinations of your edges to figure out which one has the best behavior or which one best represents the data that you have provided. So it's a little bit more like a machine learning type of algorithm, and it also uses the concept of scores instead of alpha. And so here with the constraint base, we usually set up an alpha in order to determine the strength of our confidence for the causal relationship, but the score-based instead use penalty discount, and that would be how much you apply a discount for something where it's not matching the behavior that would be expected. Okay, so I'm going to move into doing a Tetrad demo. Tetrad is a tool that has been developed in order, and it has implemented these algorithms that I have discussed with you, as well as other algorithms. I'm going to show you how to load a data set and then run the causal search algorithms on your data set, well, on the data set that I will be loading, and then running Bootstrap, and also including knowledge and running the estimator. I'll explain how some of these Bootstrap and knowledge work as we do the demo. But Tetrad here is a tool, I think. Oh, did we get rid of the link? Well, we can provide a link to where you would get access to the Tetrad tool, but this is freely available through CMU. They have a GitHub page, and they also have a page where they describe in more detail that links you to your GitHub or to where you can download a copy of the tool. All right, so I have Tetrad already launched and opened here. So you see, this is basically your canvas, which is where you would put whatever modules you need to run. And the module types that you have available to you are over here on the left side. So when we have data and we want to run a search algorithm, we'll first take our data module and double click, go into Files, their File, Load Data. And this is taking me to where I have a copy of the data saved already. So this is the data set that I'm going to run my algorithms on. It gives you some options here as far as what kind of data you have, if you need to specify missing values or comments. In this case, I'm going to keep all of the defaults because they apply to this particular data set. Click on Validate. It's going to let you know, hopefully, that there are no errors. Otherwise, it'll explain what kind of issues are in your data set so that it can't load it. So after that, you have to click Load. Done. If you want to rename your data boxes, you can right-click, say Rename Box, and I could just call this COCOMO II. You don't want to put spaces in these. They won't accept spaces, by the way. Okay, so once my data is loaded, I now want to run a search algorithm. So I grab a search, put it on my canvas here. And you now need to grab an arrow so that you can point your data to the search. And that lets the search know that this is the data it's going to run the search algorithm on. Now we double click on the search box, and it's going to pull up a list of algorithms that are available. Again, there are two types. You have your constraint-based and you have your score-based. I'm going to run a constraint-based algorithm called PC. It's one of the first algorithms that was developed. It's commonly used. So in this case, I'm going to leave most of the defaults here. I'm not going to go into too much detail of what these do, but there is a user manual that can explain what all the different options do. So again, we have your alpha for your confidence, and you can change this value, of course. I'm going to change it to 0.05, and then we just click Run Search and Generate Graph. So after it runs, it's going to give me this causal graph with the causal relationships it was able to determine from the data. By default, it gives it to you in what they call a circle layout. You can change that by right-clicking on this canvas. I'll say, what kind of layout do you want? There are a couple ones that I like to use. So one could be causal order, and just gives you an idea of what is pointing to what, or what is the cause of what other variables here. If you're looking for something specific, so in the case of my data set here, which is representative of software engineering effort, log PM is the log of my effort variable, and effort is represented in person months. So I'm particularly interested in this particular variable. So I could also say distance from selected, and then I would say log PM. And now it's going to give me how the other variables are related to the log PM variable. At my workplace, I ran the Causal Search on another type of data set. It's a little bit more bigger. So I found that this Hamada Kawaii option was really useful. It kind of does its own like clustering of the variables. So if you're really not sure what to look at, or you just have edges going in every which direction, I found that this was a useful way to look at my data also. Okay. Again, we can rename our boxes here. So I'm going to say this is PC. And I like to also put what constraint I use. So we use 0.05. We'll now run a score-based algorithm called FGES. Again, I'm going to leave, in this case, I'm going to leave all of my default options. Okay, again, we have our results as a circle. We can change the layout. And actually, let me go back to circle. All right, so for the most part, we see that FGES gave us a different model than PC in this case. And if you looked carefully, you'll notice that there are more directed orientations with FGES option as well. Again, the two algorithms run completely differently from one another. Their methodology is completely different. Now, in this case, we might see that, yeah, we're getting a lot of edges here, but you know, it's not really showing me the relationship to my outcome variable, or there are a lot of other relationships that should not really be happening. So you can include domain expertise. Let me just rename this quickly. So we can include domain expertise in these analyses using the knowledge box. So over here we have the knowledge box. Grab one of these. I'm going to point my data to the knowledge box, and so I have tiers and edges. And what it's going to do is it's going to give me all of my variables and automatically give me a few tiers here. You can add more tiers if you need them by changing your tier number here, or reduce them. So what that means is I can specify essentially which of my variables are supposed to be my outcome variables and which ones are supposed to be your input variables or your independent variables. So I can say, because I know this data set, so log PM, tdev, these are my two outcome variables, effort and schedule. So I'm going to put them in tier 2, and I'm going to put everything else in tier 1. And now I'm going to say, I'm basically going to use this knowledge for my search, and it basically helps the algorithm by me saying, this is how it should look. These two variables should be your outcome variables. So try to look for relationships such that we're having relationships that point to these two variables. Okay, so let's get a search. In this case, I'm going to use the knowledge to guide the search as well as the data itself. So you need to point arrows from both of them to the search. And I'm going to go ahead and run FGES this time. Keep all of the defaults. Okay, and let me change to circle. It's a little hard to tell, but actually it's very difficult just visually to see how is this any different from the previous run that we had. All right, so let me show you a couple more things that you can do. So if you have a graph where you just have a lot of edges going in every which direction, this one's not too bad. I've seen worse. But in the case that you did, what you can do is take a graph and just point your result to this graph. And here you want to select the display subgraph. And what you can do is say, I want to look at my effort variable and see what variables are adjacent of it or parents of it. I'm just going to select adjacent, graph it, and now I see variables that are directly either pointing to or that it points to. Or even if we didn't have orientations, in this case, we have all oriented edges, but we would see undirected edges also. Okay, one more thing I want to show you is bootstrapping. So we all know that results are highly influenced by the data set that you run the analyses on. And one way to reduce that is by using bootstrapping. So there is a bootstrapping option here. Right here, you can specify how many bootstraps to run. So I'm going to say 100. This just says the percentage resample size. I'm going to keep all of this at the default. And click run and search generate graph. All right, now we are getting all kinds of results, right? This looks like a lot. But what it's doing, because actually I didn't explain this, but we go back to the parameters. There are a few different ensemble methods here. The preserved means that any edge that had been outputted or found in your data is going to be kept, even if it showed up only once out of your 100 bootstraps. Okay, so we can use this information, and Jim's going to talk to you about how we used it. But we get a table here that looks at all of the nodes and the relationships between them. And it'll give you some more information about that node. The one that's particularly useful is the probability of no edge. So these are probabilities, and then this is going to tell us the probability that there is no edge. So notice we have size points to effort. This is a relationship that has showed up every single time, because the probability of no edge is 0. So, of course, not all of these relationships are going to be reasonable or what you're looking for. So we came up with a method to figure out where can we cut this off so that we figure out which of these results are reasonable. And again, Jim's going to go over that with you. So one very final thing I'm going to do is just show you the estimator. The estimator requires you to have all oriented edges, which is not the case here. Let me change this. I'm going to select forbid within tier. And yeah, that should be enough. So I mean, some of these factors should be having causal relationships with one another. So I'm going to try to force getting oriented edges by doing that. so that I can show you how to run the estimator. Oh. All right, my mistake. In a hurry, I forgot you have to first select or create a parametric model. Nope, not from there. All right, got rid of my search results, that's why. All right, run. Okay. All right. Okay, so we create a parametric model from that. So it's going to set up, I'm getting off the screen here, but it's going to set up saying we should have some coefficients and then we have some error terms. Okay, so now we're going to run an estimator and it's going to try to quantify the relationships mathematically. All right, am I missing something, Jim? This is not wanting to behave. Oh, I'm forgetting the data. All right, here we go.
Right.
Send it the data. I apologize. I'm trying to make sure we have enough time for Jim to go over our results with you. So let's change this layout so we can see it all. There we go. Here it has the coefficient values for each of the edges that you have here, and it's also giving your error terms. And if you look over here, you have your model statistics, and I'm not going to go over what they all mean and what kinds of values you need for this particular presentation, but you do have access to your statistics here. So let me summarize just a few things that we went over. We have in the slides an image of the tool chain. This is the simplistic version of what you would need. You have your data loaded, you would run your search algorithm, you have your optional knowledge if you need it or want it to help guide the algorithm. We talked about Bootstrap and the result that you'd get. So we're calling this an edge probability table. What's particularly of interest, I guess, at least for this presentation, is the probability of no edge, as I discussed. This is going to be important for the work that we do later that Jim's going to describe. And we talked about causal estimation, so we're trying to quantify the relationships. And these are the statistics. You can get more information from these references that are in the bibliography. And I just want to summarize with causal inference is really helpful and useful for 3 reasons. So 1, you can define your causal relationships from observational data versus running experiments, which again, in a lot of cases, running experiments is cost prohibitive or impossible. And it's using interaction among variables to determine those causal relationships. So it is more advanced than correlation in that way. And Tetrad, the tool, allows you to run these algorithms very quickly, very easily, very efficiently. and people have used on really large data sets, and they found that it gives you the results very quickly. So we would highly recommend for you to at least give it a try. So let's transition to the next part of our talk. And I'm going to hand it over to Jim, who's going to explain how we actually applied causal inference to data that we have.
Thank you, Anandi. Can you stop sharing your screen? Thank you. So I'm going to pick up from where Anandi left off with slide 30. So I'm going to talk about what happened when we applied causal analysis to our two data sets. I'm going to first talk about the data sets, then talk about our search results, and then end with our causal estimation results. And then I'll go over some conclusions and how to get started with causal inference. So we used two data sets. One was a COCOMO II calibration data set that was used to derive the COCOMO II software cost estimating model. These came from 16 organizations, a bunch of different application types, had variability in all 26 variables on 161 projects, and reference 6 is the COCOMO II book. The other is the COSYSMO 3.0 calibration data set. This is the data set I used in my thesis. This covers various types of systems, and with over a factor of 100 size difference in the data. We have variability in all 18 variables and 68 projects. And this is a reference to a paper on COSYSMO 3.0. Let me mention something that to set up what you're going to see. COCOMO 2 has 161 projects and 26 variables. That's 6.5 projects per variable. COSYSMO 3.0 has 68 projects and 18 variables. That's 3.9 projects per variables. The COCOMO 2 is kind of more powerful in this regard. It's got, you're going to see that in general, it has more results and more statistically significant results than COSYSMO 3. And this is why. It's because of the ratio of the number of projects to the number of variables. So let's start looking at our results here. This top part, what I'm going to do is I'm going to go forward to slide 34, and then I'm going to come back to this. So here are the problems that we had when we just simply ran Tetrad in a kind of a simple-minded fashion. And these two searches, or these two search results, are done under the same circumstances, except for the penalty discount algorithm, parameter to FGES. So we have a less strict search on the left and a more strict search on the right. Now on the left, we get lots more edges, but we get some edges that are just not reasonable. So for example, there's an edge here between log size and MIGR. MIGR is the migration difficulty of the system. Is it a new system, or is there lots of old systems that need to be migrated to? And this graph says that log size causes the migration difficulty. Well, that's not true. Migration difficulty is an aspect of the problem itself. So this cause is non-plausible. All right, so if we make the penalty discount more strict, we get rid of a lot of that non-plausible stuff. But what we find is we only get one direct cause of effort, whereas over here we had two direct causes of effort. So using this in a simple way causes us some difficulties. So back on slide 33 here, That kind of summarizes the first half of this slide, except that we have relatively few data points. So we, working with Mike Conrad, invented an approach called weak signal analysis. Because that's the way we would characterize our data, we want to pull out the weak signals in our data. And these are based on that probability of no edge table that Anandi showed earlier. So we're going to kind of search through that table and use it to eliminate edges. But first, we're going to do something called, add something called null variables. So for each original variable, which is one column of the data, we're going to add a null variable column. It's a copy of the original, but randomly sorted. So this is like a really meaningless data. The null variables are meaningless because they're sorted into random order. All right, now we do our causal search with Bootstrap, and we look at each edge that terminates on a null variable. All right, and we call these edges terminating on a null variable a random edge because they're going to random data. And we look at the probability of no edge for each one of these edges. And there's a lot of them. So we say, well, we'll allow the top 10% of those in. So we set the 10th percentile of these random edge probabilities of no error. And 90% of random edges will have a higher probability of no edge. And we discard all edges whose PNE is greater than this 10th percentile threshold. And we also discard all null variables, and we discard any random edges. And now we can go to slide 35. This is the result of doing a WSA search, or search and an outside algorithm on the the COCOMO II data set. So we have everything that's here is a direct cause of log person months, that is to say effort. So we have size, team cohesion, platform volatility, reliability, storage constraints, time constraints, product complexity, process maturity, and risk and architecture resolution. That's a number of direct causes, but it's much less than the 26 variables that exist in COCOMO II. Now on systems engineering, we have just two direct causes of log effort. This is a level of service requirements parameter, and we have the size parameter. And those are the only two direct causes of effort for COSYSMO 3.0 data. All right, now I'm going to talk about the specifics of determining cost estimates. And what we're going to end up with is something called a mini model, those are models that have the same structure as the original estimating equations, but many fewer parameters. For example, here, only 2 parameters for COSYSMO 3, and here only half a dozen parameters or so for COCOMO 2. So that's what we're going to end up with. And we kind of look at the existing COCOMO and COSYSMO models. And we immediately run into a problem because some of the parameters in these estimating models are in the exponent. They're what these models call scale factors, and they go into an exponent. All right, so that isn't going to work in Tetrad as it is. So we take the logarithm of the estimating equation. So then instead of size, we have log size. And for COCOMO 2, we have log person months and so on. And now the cost drivers, which were multiplicative, are represented as additive variables. And the scale factors, which were exponents, have to be treated fairly specially. So the scale factors are multipliers of log size. So instead of the scale factor itself, we multiply the scale factor times log size, which is kind of like if you take the size to the exponent and then take the log of that, this is what you'd get here. we forced cost predictors to be independent of each other. In her demo, Nandi did this at one point. She flipped a switch that says all those tier 1 variables have to be independent of each other. We applied our weak signal analysis to get a plausible causal graph. We discarded any variables that have no edges. And then Tetrad, as Nandi demoed, has a estimation capability built into it. And we can get coefficients and intercept. And you saw her give an example, but unfortunately, there's a little problem with the intercepts, which I'll get to in a minute. So here's a tool chain for applying weak signal analysis. In the top 3 boxes, you use the same tool chain that Anandi talked about back on slide 23. All right, now, so we have this search result here. Now, outside Tetrad, we perform our weak signal analysis and on the P&E table, the probability of no edge table. And this is kind of just repeats the description of the WSA method that I talked about before. You look at a 10th percentile trim threshold, delete all edges with lower probability, delete the null variables, delete all variables without edges. And now, so this is outside Tetrad. Then you import the resulting graph back into a Tetrad directed acyclic graph box. And then, as Anandi did in her demo, you add a project model and then an estimation model. And this then is the mini model that we get in from using our weak signal analysis approach. So here's the resulting COSYSMO 3.0 estimation. There's coefficients and there's means. There's some error terms also. Let me note that for COSYSMO 3.0, if we look at those statistics of model fit, this one isn't so good. It's probably poor to fair. Now, the problem comes in here in this mean. So if I just read that off, it would be, here's log effort equals this times log size and that to the LSVC power plus 4.2838. So we take the anti-log and we get effort equals size to this power, 1.357 to that power, times 10 to the 4.2838. Well, this number is bigger than 10,000. And that means all our efforts would be in the general vicinity of 10,000 person hours. But that doesn't work. The problem is that the intercept that Tetrad found is the mean of the log effort values. But what we want is the log of the mean of the effort values. That is to say, the mean of the log is not the same at all as the log of the mean. So in this case, we have to go outside of Tetrad, do a separate linear regression for log effort against log size in LSVC. That yields an exponent for 10 of 1.805, which is much more reasonable. That turns into a multiplier of 63.834. And that's a pretty decent mini model. Look at size, look at the level of service requirements, and this is 63.834 hours that you multiply by. On COCOMO II, if you delete the ones without edges, let me mention the model fit statistics lead to the conclusion that this model fit is fair to good. They have effort. We even have an edge to the time of development. This is calendar months. Where do we end up with this? So on causal search, we discovered that a straightforward use of causal discovery algorithms may result in little information about cost-causing factors. We think our data sets just aren't big enough. The weak signal approach enhance the results. We got additional causes of effort and duration while minimizing spurious correlations. And this is a principal approach methodology. It tells us where to do that cutoff in the PNE table, and that trims the results of a Bootstrap search. And we identified specific direct causes for the two estimating models. And this is where action has been shown statistically to cause the cost or schedule. Not just correlated with the cost or schedule, but to cause the cost or schedule. And so this is pretty good results. We have multiple application types, multiple organizations. And along the way, we investigated what search algorithms to use and what parameter values. So on causal estimation, we developed a methodology for generating mini models based on data sets that deliver plausible results, based mostly on features built into Tetrad. And if your data if you don't need a logarithm, apply logarithms to your data set, then Tetrad can deliver completely an off-the-shelf model. And our observations is modestly fitting with not as good predictions compared to the original model. If you look at the full COCOMO II estimating model, that actually does give better predictions in general. All right, so now we'd like to some extent, we're hoping that after seeing this talk, you're going to get started yourself with causal inference. We encourage you to try Tetrad on your data, find out what the causal factors are. If these simple results are unsatisfactory, consider using the weak signal analysis. It should be applicable to an organizational project database of moderate or larger size. You can get Tetrad. Reference 3 is how to get the Tetrad software. And reference 8 is how to get the Tetrad manual. And training in causal discovery in Tetrad is available. All right, so this is our bibliography, and I think this is a good point for us to open it up for questions.
Sure, thanks a lot, Jim and Anandi. We do have one question currently, and again, folks, if you have questions, go to the Q&A tab of the webinar, and you can enter it there. Daniel Beatty was asking, how similar is Tetrad to tool sets like Weka? That's actually a machine learning tool set. I know Windsor Brown has chimed in and said it's a machine learning tool set. It doesn't really do any causal analysis. But maybe, I don't know, Jim or Anandi, if you could talk to if there's any relation of, whether maybe those two tools are ever used together, or if they have been used in a complementary fashion. Not sure if you had any comment there.
I myself am not familiar with Weka, and I would, I think Windsor, it looks to me like Windsor gave a pretty good answer.
Yeah. Yeah, it is definitely it's a machine learning tool set. There's a website on it, actually, that's given in the question as well. Yeah.
Right, I've heard of Weka a couple times, and I will agree with Windsor's answer. So Tetrad is built specifically to implement the causal algorithms. So algorithms that the researchers at PMU, University of Pittsburgh, and even others have come up with in order to find causal relationships from data. That's all in Tetrad. So it's very specific to causal inference. I don't think Weka has implemented, at least I have not heard of them implementing these algorithms. So that would be one major difference between the two.
Right. Okay. Yeah, I think when you mentioned a couple of references, I think there's some bio-related research being done with causal discovery, I think, as well, right? At least it seems like there is. Hey, we have a question from Tom Phillips. He's asking, is it possible to model feedback loops between causal factors in Tetrad?
I think I can answer that. If you're talking about a time series, then yes, Tetrad does have the ability to analyze a time series. On the other hand, if you're talking about static data, that time is not involved, then the answer is definitely not, because a causal graph by definition is acyclic. So there's no feedback loop in it.
Right. Okay. Okay, and I think that's it on the questions. We do have one question actually that, sorry, I meant to start off with. This is actually, we wanted to get a quick poll, good time to do it. Just of the attendees, if you would let us know which professional organizations you are a member of, that would be great. Okay, fantastic. I had a question, Jim and Anandi. I don't know if it's a valid question or not. Is this, have you had once you come up with some of these factors and coefficients and everything, is it like sort of a subsequent step to try to apply it to projects and see what the results are like, or is that something that you've tried, or how does that, where does that kind of fall in the spectrum of this, looking into this sort of thing?
So
that question makes sense?
I'm not sure I understood it completely. Are you talking about having a model, then generating?
Yeah, once you have the
data, and then
estimation model, I was wondering, yeah, whether you actually what do you do with the model after you come up with one? How's that for the renewed, for a different way to state it?
Well, what you would have then is a cost estimating model, which you could use to estimate your next project. And so,
Right.
Yeah.
So I was wondering if you had, started to apply those, or had folks that have been applying your models at all, or have seen any results with it.
I haven't.
So if you mean,
go ahead, Anandi.
Go ahead. I was just going to say, if you mean from this research that we have done, I'm not sure if anyone has applied it. We have presented this work at a couple now venues that are specifically put towards software and systems engineering cost estimating. However, in this field of software and systems cost estimating, a lot of times data from different environments behave differently, or different environments just behave differently. So one model might not fit somewhere else. We're hoping to encourage people across all fields, but especially in the software and systems engineering, to look into using causal analysis. So I did mention that I'm now working at Technology, and I'm going to be I've already started running it on a data set that I have access to. My employers already have a model based on this data set that they have been using since before I joined. But hopefully if I get something that works well, that's different from running these, then we may look into using that model instead in the future.
Okay, cool. Thank you. There was a question, actually it's not exactly a question on the topic. Somebody mentioned there's membership in the National ACM and LA Metro IEEE Computer Society. Equate to, is it the same as LA ACM chapter? I don't believe so. I think they're explicit memberships. The national membership doesn't automatically put you into a local chapter. So it's a quick answer on that one. Okay, any other questions that folks want to air on the webinar? Okay, Jim and Anandi, would this be a good point. Oh, hold on one second. I think we might have one question potentially coming in. Just give them a second here. All right. Actually, otherwise, would this be a good point to break into? I'm thinking that it would be great if we got onto the regular Zoom session afterwards, just to make sure folks wanted to ask you questions more personally. We have an opportunity to do that, and if there isn't, that could be a quick call, but a quick Zoom meeting. But otherwise, it would be a great way just to make sure anybody that wanted to have a chance to say hello, Jim and Anandi, have the chance to do that. Folks on the call, you'll see the link in the chat there that will take you to the Zoom session. So what I would encourage you to do is cut and paste that, so you have that. We'll leave the session up for just a little bit. So what you all could do is go to that session, but you'll notice that you'll probably be waiting in the waiting room for just a second until we finish this call and move over to that one. So make a note of the that link there, because it'll disappear on you when we close this session. And actually, we have one question. One more question actually from Andrew Osodolor. And I think a few people have dropped off, but we can go ahead and ask that, Jim and Anandi. It's, are you aware of causal inference being used in criminal justice?
Oh, what an interesting question.
Yeah, that's what too.
Well, there's two things I can think of. One is that law has a very well-developed concept of cause, which is certainly its foundations are not based on statistical causality. So that would seem to rule that out on law. On the other hand, I do hear news stories about, for example, in determining whether, in a judge determining whether or not to give bail, he might rely on a piece of software to judge the risk of letting the defendant go without bail. And that kind of software, one could look at, do a causal analysis on the underlying data, assuming the algorithm was, built directly off of a data set. And so that would be a very interesting analysis to do.
True. Okay. All right, so why don't we go switch over to the other webcast. And Anandi and Jim, are you ready to join us over there?
Yeah, momentarily.
Yep.
All right, we'll see you there. Yeah, thanks for the presentation.